Hello. Everything should be okay. Let's see.
Yep.
Yep. You can hear me and see the desktop. Okay. So let me bring up Windows. Okay. Hello. All right. We're going to continue today to play with the examples we were playing with uh, on Monday. So let me download language 8. And what I want to do is we were playing with the make adder and make counter, and I wanted to compare them to the JavaScript version some more. Because after class, I've figured out some more about the JavaScript versions. I realized some things I hadn't seen before. Okay, so and I think this is worthwhile because JavaScript, to, to exaggerate a little, to not exaggerate at all, JavaScript is an incredibly important language right now. It's not anybody's idea of an elegant language, but it's tremendously useful. So right now, besides knowing Java, the probably the next best language you can learn is JavaScript. So I think it's actually a good idea to kind of see how JavaScript is actually surprisingly close to what is our language 8 is a baby version of Scheme, and JavaScript was famously modeled on Scheme, so they actually come from the same base. They're both versions of Scheme, uh, and JavaScript is actually very close to Scheme, but with C syntax. We've kept the scheme, we've kept the Scheme syntax. Our language 8 is a simplified version of Scheme. Their JavaScript is Scheme with C syntax. It's not really simplified because it's a sophisticated language. JavaScript's a sophisticated language, but it's essentially Scheme with C syntax. So JavaScript and language 8 are a lot alike. They both do this idea of closures. They implement closures pretty well. Okay, now here, one of the things I remembered was that there's a visualizer for JavaScript out there. So I took the make adder and I put it in the JavaScript visualizer. Okay. And what I do is it's interesting to compare this visualizer with our version of language 8. So like down here, I have this you know, this version of Java 8, which kind of is a visualizer because it lets us see the output of the language running. So what I'm going to do is run this in a command line, run language 8 in a command line with the, I'll do make, which one am I doing over here? Make adder. Okay, so there's a language 8 version of make adder. And if we open it up in an editor so we can see it, okay, there's make adder in code. There it is in JavaScript. Okay. And then if I run it, I would run it here. Okay. Uh, I think I mentioned the other day is if you compare this pretty printed version of it to the JavaScript, they look a lot alike. Okay. They look, yeah. If I, yeah, make adder takes a parameter X and it returns a function that takes a parameter Y. So it returns a function, takes a parameter Y, and it just returns X plus Y. Okay, then it returns X plus Y. X is coming from the parameter to make adder, and Y is the parameter to this function that's returning. So it's a function that returns a function. So it's a function that returns a function, and then the function returns a number. So make adder is a function that returns a function that returns a number. Okay, and the same thing here. Make adder returns a function that returns that number x plus y. Okay. And it's a function factory. The way to think of it is it makes adders. So like when you call make adder with 5, you get a function that adds 5 to anything you give it. When you call make adder with 10, it builds a function that adds 10 to anything you give it. Okay, same thing here. So add 5 and add 10 are the functions that add 5 and add 10. Okay, so if you call add 5 with 2, you get back 7. So I rewrote the language 8 version to look just like this language. Oh, and remember, I got this code from the Mozilla website. See, so what I did is after class, we looked at it in class the other day as essentially as coming from the Mozilla website. Okay, so remember, this is the documentation at Mozilla on closures in JavaScript, and we were doing this example here. But we just kind of did this example. We compared it to language 8, but then I realized I could put it in the Java visualizer. Okay, and I want you to see how the Java visualizer visualizes this compared to what is visualized over here. So I took this code here I just copied and pasted this code here into the visualizer and created it as a visualizer site, a visualizer page. Okay, now here I've run the code here, so this is it running. Okay, and over here I can run the code by clicking on visualize execution. Okay, now the visualizer is actually real kind of interesting. It does something I hadn't looked at this Java visualizer in a couple of years. Actually, I've used the JavaScript. I use the Java visualizer a lot in my classes, and I've used the C visualizer. I don't teach a class in JavaScript, and I hadn't actually looked at how the JavaScript visualizer works with JavaScript, and it kind of surprised me when I went back and looked at it, how it visualizes JavaScript. Okay. Look at this. This is really kind of interesting. That's a function, right? Notice that the value of that variable is a pointer to the function. See it's actually treating it like a first-class object. The variable is a function value. So it shows the function over here in the heap, which is very kind of quirky. It's actually fairly accurate, because that's exactly how we think of it, is that the variable is a name for a function value. Okay, and there's the function value. There's the code. That's an IP, an instruction pointer. The value of a variable is the address of its code. Okay, but I've never seen anybody visualize it that way. So the name of the function actually points to its code. Okay. Now suppose you call that defined make adder. Now call make adder and define add 5. Now when you call make adder, you jump. Okay, you step in. Okay. Now when you call make adder, you step to line 3. That's the first line of code, which is just a return statement. And so the next state says that you're returning. Oh, notice that the parameter x was 5. See, when we stepped into 5 was the parameter to x. Okay, so that's the parameter. Now the return value is this code. See, it's returning that function, so it's showing you pointing at the code. Okay. Yep. Because a function value is the address of the code, but they're showing as if the code was an object in the heap. I'm not sure that's really quite accurate, but a function name is a reference to the code of the function. So it's actually showing us that. So then if we do the return, see add 5 points to this function. Notice that function's a subset of that function. If you look carefully, that is just a copy of that. Okay, but now it's its own function value. So in a sense, it's really pointing inside here, kind of. But we want to talk. But one of the things I want to talk about is how accurate is this? See, in a minute, we'll think about this and think, yeah, how accurate is this? Is this really telling programmers the truth? You know, what's right here and what's wrong here? And it turns out that there's a little bit right and a little bit wrong. Like kind of like one thing you could say it's a little bit wrong is, why did that code get copied down here? It's that code right there. See, function y returns x plus y. Notice that when you put it down here, what the heck is x? See, in a way, there's a little bit right and a little bit wrong. When you say that add5 is that, well, okay, what's x? See, now you have very much a free, open function, an open function with a free variable. Now over here, we have an open function with a free variable, but it's closed by that variable there. This free variable is closed by that guy. When it's down here, it's not at all clear what closes it. Okay. Now, in the case of add5, it's actually being closed by the value of x being 5. See, really, now one of the things that's wrong here is this add5 isn't a function, it's a closure. Now, if we go over here and look at our equivalent of add5, there's our equivalent of add5. See, there's add5 in the environment. See, here he uses the word frame for environment. That's not unusual. If you look in the literature of people who study programming languages, a lot of people like to use the word frame for the word environment. Majority of people use the word environment, but there's a small number of people who call them frames, a frame of reference. I think they got the word from, it's the frame of reference for, or the reference frame for these variables. Okay, yeah. It's the environment we're computing in. It's the frame of reference of where you get your values from. So, I mean, I don't know if some people call them environments versus frames. Some people call them frames. Oh, no, I don't want framework because this is very much, I probably won't get anything. Oh, how are environments, closures, and frames related? Oh, that's a real good question on Stack Overflow. Yeah, how are environments, closures, and frames related? And the answer is environments and frames are the same thing, and a closure is a pointer to an environment. A closure, I don't know if the person who gives the answer is going to do it right, but the answer was environments and frames are just the same thing, and a closure is a pointer to an environment and a code. So a closure is two pointers, one to an environment and one to, okay. Now over here, add5 is really a closure. Now over here, see, add5 is notice that, see, what we point to is an IP-EP pair. The IP, they're essentially showing just the IP, the instruction pointer. That is what the IP is in ours. The IP is the code. Now, what he's not showing you here, and I think it's a big mistake, he should have two arrows coming out of there. One arrow to the IP and one arrow to a little box that says X is 5. See, that's when there should be a second little arrow coming over here to a box that is the environment, the frame that was, oh, and what frame is it? Let me step backwards a minute. It's that frame there. See, that's the frame. Now that frame there in our picture, if you look real carefully, is this guy here. That environment is that box there. That frame is that environment. It's the one that holds X is 5. If you read this, if you squint and look real carefully, the visualization over here matches up to the visualization over here. The visualization over here is actually a little bit more accurate than the visualization over here. But the visualization over here is a GUI, so everyone likes it better. Okay, this is a GUI visualization, but but as we'll see, it's kind of good and kind of bad. And this is a more of a text-based visualization. It's kind of good and it's kind of bad. I think this one's a little bit more accurate. The problem over here is when I got to the IP-EP pair, I couldn't show the two pointers. Okay, he could have here. If I step forward here, okay, there's the pointer. There, he's got one of the pointers. That's the IP pointer. Boy, he should have he should have kept this box and moved it over to here and then made add 5 point to that code and that box. Or he could have left the box right there and had a pointer to that box down here. So this is the frame. Okay? And we call it an environment. So this box here is literally that box there. It holds X with 5, holds X with 5. Okay. This is what's going to get returned to add 5. So that's the next line down. See, now add 5 holds an IP-EP pair. The IP, just like over here, the IP is exactly to that code. If I showed you what that IP is, you'd see it's a pointer to the abstract syntax tree for that lambda expression. That's exactly what it is. See, that's the lambda expression. And we saw that in language 7. If we go back to language 7, when the val-Ls were only IPs, you'd see that lambda expression in there, just like in here. Like let me go back and remind you exactly how language 7 looked. So let me download language 7, because language 7 actually visualized exactly this way. Language 7 showed us those trees, abstract. Here he's showing it as source code. We showed it we showed it as source code also. Like, let's go back to language 7 and just real quick look at a visualization in language 7. Because it's surprisingly close to what he's showing in the JavaScript visualizer. So let me just go back and do a real quick, one of the examples in language 7. Let me clean off I need more and more monitor here. Let's see. Okay, open a command line for running a language 7 program. Here's the language 7 interpreter. Okay, let me think which would be a good example to use. I don't remember which one of these would be a good one. Let's try. Let's just try demo. Let's try demo 7. Okay. Here. Just look. See, value L points at code. See, I have a variable that points to a lambda expression. Okay. If I translated this, I should have translated all these into a JavaScript example. See, I have this in language 7 and C. I wonder how hard it would be I'd probably turn this into a JavaScript version and then visualize it and see that it looks just like this. But these are not closures. See, language 7 didn't do closures. So a first class variable in language 7 is just like in C. It is just a IP pointer, an instruction pointer. The variable points at the source code, the abstract. In our case, it's pointing at the abstract syntax tree. Let me see. Let me think how hard that would be to turn into JavaScript real quick. This was a program that, see, there's a squaring function and a cubing function. Okay, squaring function in JavaScript, delete the return type, delete the return type, delete the declare here. Oh, now it's JavaScript. That's all. Okay, that's JavaScript now. Just delete the types, and that's JavaScript. The squaring function takes in an x and returns x times x, and the cubing function takes in a y and returns y times y times y. Okay, so there's JavaScript. Okay, now we had a function that we called the choosing function. the choosing function did a return of either F1 or F2. Now here, see, I don't need any of this type information. So I can turn this into JavaScript and make it a JavaScript choosing function by just basically deleting almost all the type information. So see, F1 was a pointer to a function that took in an int and returned an int. Well, in JavaScript, F1 just is F1. That's my second parameter. F2 was a pointer to a function that took in an int and returned oh boy, I can't even remember how to read that. Oh yeah, F2 is a function, is a pointer to a function that takes in an int and returns an int. So there is the, now in JavaScript, F2 just be F2. Okay. Now this was the return type of choosing. I don't need that anymore. Oh, now it's JavaScript. Okay. The choosing function takes in three parameters, a z, an f1, and f2. If z is negative, you return f1, otherwise you return f2. Okay, so there's the choosing function. And I don't even need to make it multiple lines. If I'm going to make this JavaScript, I can just compress this and just make it a one-liner. Okay, so there it is in JavaScript. Okay, now f uses the choosing function. F takes in an input, and then it chooses, depending on its input, between the squaring and the cubing of the input. So if you give, the F was, if you give it a negative number, it chooses to cube it. But if you give it a positive number, it chooses to square it. Okay, that's how that worked. Turn this into JavaScript by just deleting the types. Remember, JavaScript was scheme in C syntax. So notice that to turn the C into JavaScript, I mostly just delete the types. Okay, and that's JavaScript. Okay, there's a one-line job. So F is a function that takes in a W. What it returns is it uses the choosing function based on W to choose either the squaring function or the cubing function, and then it applies the it applies the returned function to W. So it uses W to choose a function, and then that function gets returned and it's called on W then. So W is used to choose the function, then the function's applied to W. Okay, so you end up cubing negative numbers and squaring positive numbers. Or the other way around. Which one I do it? Negative numbers choose the first function. So negative numbers are squared and positive numbers are cubed. So let me see here. The choosing function takes in an F1 and F2 and a Z. If the input number is negative, you choose the first of the two functions. So here if this is negative, I square it. And if it's positive, I cube it. So the answer is always positive. Okay. Now, my main method. Okay. Now, this is where there is no printf, I don't think, in C# in JavaScript. In JavaScript, when you want to print something, you do what is it? The console.log. Okay, console.log f of 3. Okay. Okay. All right. And then this was just a comment. This showed the language 8, this language 7 version of it. Now, actually in JavaScript, there is no real main method. So really what I actually should do is delete that. And that's just at the top level. I'm just going to call these, see? Okay, I think there it's translated into JavaScript. So that would be demo 7.javascript. Okay, so I think that's JavaScript. How do I find out if it's JavaScript or not? Let's load it into the JavaScript visualizer. Okay, so it's called JavaScript Tutor. See, it's called the JavaScript Tutor. That's the site. It's actually called the Python Tutor because it was originally written for Python. Then they expanded it to do JavaScript and a whole bunch of other languages. So it's actually now a bunch of visualizers: Java, JavaScript, C, C++, Python, I think Ruby. Oh, it's right here. Python, Python 2, Python 3, Java, JavaScript, TypeScript, Ruby, C, and C++. Okay. We're interested in this one. Okay. Visualize. Okay. Syntax error. Where did I make a mistake? What did I? Oh, I have to say function. I have to say function square root. I think so. I think I think I have to say these are function declarations. So let's see if that fixes those. Okay. Let me go back and before I forget. Those were function declarations, so you have to say that you're declaring functions. Okay. All right. Now, see how square, cubes, change, but see how they are variables pointing at their code. See? Now, if I ran the language 7 version of it, we'd see that, oh, over here. See, here's the language 7 version. See, square root points to its code. See how square root, cube, choose, and F all point to their the code value. These are tagged variables. So you ignore that. See, the tag is lambda. So you ignore that, you ignore that, you ignore, and that's the one you look at. They're actually doing the same thing here in JavaScript. These are tagged values also, but the tag is hidden from you. So the tag is a very low-level thing in JavaScript. You don't see the tags, but in fact, they're actually doing the same thing. See, we're inside the interpreter here. So we're actually inside the interpreter here. Here, they are visualizing the language. So they're not going to show you how the language is implemented in the interpreter, but the language thinks of SQ as a variable that points to a function. And cube is a variable whose value is a function. Now notice that the C version would never, okay, now if we go, here's the C version, and I can load it into the visualizer also. It's kind of, I mean, this is what you should be doing, thinking this way. Visualize all these things. I want the C tutor. Okay. Same code, C, JavaScript, language 7. Visualize it in JavaScript. Now visualize it in C. One thing that's interesting is the names SQ, CB, F don't show up anywhere over here. In a language like C, you tend not to think of SQ as a variable with a value. You think, oh, it's the name of the function. And that's actually one of the problems with the way we teach programming languages. We teach you these old-fashioned languages, which are really not the right way to think about modern languages. You should think of SQ as a variable whose value is that function. And the JavaScript tutorial, the JavaScript visualizer actually says SQ is the name of that function. It's the function is a value, and this is a name for that value. In C, you tend to just think, okay, SQ is defined over here. CB is defined over here. CH is defined over here. Here are my variables. So if I start stepping through the code, notice that F is the function I called, but it's not thought of as a variable. W is the variable. So W gets a value, not F. F is just, that's the function I call. I'm calling the F function. Okay, actually, and I should have, I was in the main function. If I go back a step, see, I start in the main function. Here I'm in the main function, and then I called the F function and passed it parameter -3. Okay, F is going to call the choosing function. So now main called F, F called choosing. Notice that main, F, and choosing are the names of functions, but they don't show up other than their names here. Over here, when I start stepping through the code, see, I'm in the F function. See, notice here, let me step one more. Okay, this picture is that picture. Main called F, F called choosing. My top level called, my global frame called F, and F called choosing. So I started off in the global frame. That's like main method. I called F with parameter -3, and then I called choosing with these 3 parameters. See? Now notice here, what's F1? It's a pointer, and they just put a question mark there. Well, no. See, they don't tell you what it points to. They don't know what to point to in C. See, a function name. See, here, F is a function name. They're kind of hiding from you what F is because they don't know what to show you. It's a bunch of compiled binary code. Okay. Now, here it's a bunch of compiled binary code too, but you think of it as that source code. Here, we think of it as an abstract syntax tree. Okay. So a function name, in our case, points to an abstract syntax tree. In the case of JavaScript, it actually is pointing to binary code. The JavaScript's got a compiler, a just-in-time compiler. It's a just-in-time compiler, a JIT compiler, but this code is actually compiled. But the visualizer shows you, well, it's a function. So it shows you the source code. C doesn't know what to show you. It's F is a function. It's over here. You look for it over here. F1 is a pointer, and at this point, they don't know what to show you F1 points at. They don't really know what to do. See, notice I'm calling square. That's because I returned one of these pointers, and one of those pointers was pointing at the squaring function. And the C visualizer really doesn't know how to show you what this code is doing because it's manipulating function pointers. It just doesn't really know what to show you. Okay. We called the squaring function because we had returned from the chooser the squaring function. Okay, but you don't really see that happening. The chooser chose one. Let's see. The chooser, it doesn't even show you what it returns. See, the chooser is returning. It's returning one of these 2 pointers, and the visualizer doesn't even show you which one it's returning. See, the visualizer has no way of showing you. It doesn't even bother to show you whether it's returning F1 or F2. Okay. The Z was -3. If you have a negative value, returning F1. So it's returning F1. And I know that F1 was squaring because I can see over here, F1 was the first parameter the choosing was the squaring function. But notice here, it's just all a mystery. F1 points, I don't even know what that's an icon to. Yeah, it's a pointer, and they just show you some dumb little icon in here because they don't know what to show you a pointer is. Here, function pointers point to code. Okay? And over here, function names point to code. That's the more modern way to think of it. A function name is a chunk of code, except that when we get to language 8, a function name isn't a chunk of code, it's a closure. It's a chunk of code with the environment that closes it off. And that's where over here, they kind of failed. At this point, they see their C tutor, their C environment doesn't know how to show you functions at all. If you visualize simple functions that don't need closures, this JavaScript visualizer works well. But when the JavaScript visualizer tries to visualize closures, it starts failing. And this is a failing of the computer science community. It's not building good tools for teaching this stuff. The C tutors should be better. The JavaScript tutors should be better. We just don't have good tools for showing this stuff. It wouldn't be that hard for this thing to point to either have two arrows. What it really should have one arrow pointing at a box. The box would be the IP-EP pair. See, this is an object with two references in it. So it's one object. See, it's one pointer. You point at the IP-EP object. If they did this right, this would point to a box that holds two arrows, one arrow to this function and one arrow back at this environment, this frame that they deleted. They shouldn't have deleted this frame from the picture. And at this step, this should have pointed at a box, the IP-EP pair, the closure, and that box would be two arrows, this arrow at the function and the other arrow pointing back at this deleted environment, which has disappeared on us. Then that deleted environment would solve the mystery of where's this X at? This X is in the environment that they deleted here that this thing is really pointing at. In the interpreter, this thing really is pointing at, just like the JavaScript interpreter is acting just like our interpreter over here. Add5 is a closure. So add5 points at a thing that holds multiple pointers. And in a minute, I'll show you what this looks like in the JavaScript console in Chrome, which shows you it right. Okay, so that's one of the things I want to show you is that if you open up the Chrome debugger, it doesn't show it to you as elegantly as this, but it does. It's more back like this. It shows it to you more like this, but it's correct. Okay, but then you have to be inside the Chrome developer debugger. Okay, I'll show you that in a minute. Okay, so notice we're same code, the same piece of code. Well, here I've got the same code in JavaScript and language 8, and here I have the same code in JavaScript, C, and language 7. Okay, and I want to compare all these things. Comparing is where you learn. When you can say the same thing is used this way over here and the same thing gets treated this way over there, when you can make those kind of subtle comparisons of the same thing in two environments, that's when you can start really understanding this stuff. Okay, same code in C, JavaScript, and language 7, 3 visualizations, a C visualization, a JavaScript visualization, and a language 7 visualization. In this case, the C visualization is really a mess. The JavaScript visualization is exactly like our language 7 visualization. They coincide pretty much exactly. Okay, these variables point to the code. And you can look real carefully. What's squaring pointing at? Lambda x, multiplication of x and x. What's squaring pointing at? Square of x is x times x. What's CB pointing at? Lambda y, y times y times y. What's CB pointing at? Function of y returns y times y times y. Okay, see. What does CH point at? CH points at lambda z f1, f2. If z is less than 0, return f1, else return f2. Well, what does CH point to here? Function CH of z f1, f2, return if z is less than 0, f1, else f2. See, same lambda expressions. Okay, so this is kind of a nice visualization of what we're showing over here. Okay, then you have these other variables like, see, this frame here is actually, let's see. This is the, I'm not tracing these things in the exact same order. See, here it's all shown at once. Here it's shown over and over again, because over here we have to redraw the visualization each time we step through. So each step of this is one chunk of what's listed over here. Here it's all just listed. See, it's like this goes on and on and on, because these were the steps of the program. So you have to figure out, see, as the program executed through its steps, you have to figure out, this was step 1. Actually, I might be able to line them up. Go back to the beginning. Now, see here, they did something funny. They declared all these variables at once. They didn't step through and define this one, this one, this one, and this one. So you get all these variables declared at once. In the code over here, in our interpreter for language 7, what it did was it first declared SQ, then it declared CB, then it declared CH, then it declared F. So you see the global frame building: SQ, SQCB, SQCBCH, SQCBHF. Okay, this is this picture. Okay, so they start off with all 4 functions defined. That's their choice. They didn't step through. They did not step through 1, 2, 4, 6. See, their arrow, if you go back to the beginning, their arrow started at line 8. Why? I don't know. Yeah, like, why did they start at line 8? Why didn't they start at line 1? Line 1 would have declared SQ. Line 2 would declare CB. Line 4 would declare CH. Okay. Line 6 would declare F. Why did they skip over those? Somehow that's what they chose to do. Here, we went through that line of code, that line of code, that line of code, because you had to declare those variables one by one. And then you see the global environment. He calls it global and frame. We called it global environment. Okay. The global environment grew to there. Okay, so now we're at that point. So that's where they start. That's where we're at after several lines of code, after 4 lines of code being executed. The next thing they do, well, they do line 8. Okay, line 8 is this guy. See, the global environment with W hanging off of it. See, the activation record for F, see, this is a function activation record with W bound to 3. And that's chained to the global environment. So here's the function F activation record. So we're at line 8 of the code. We're executing this function call in here, F of 3, -3. So we're executing that function call. So we're calling F. Okay. So we're actually inside here. We're inside the execution of F with the W bound to -3. That's what we have over here. Okay. All right. So what happens when you do the next step? Now this thing's going to return. Okay. Now we're at line. Okay, we have to read this real carefully. Oh, F calls choose. I'm sorry. We were at lines. See, we're in F. We're still executing F. F calls choose to decide which function it should call. So you can say line 6 called line 4. So F from line 6 called choose at line 4. Over here, that should be this one here. Okay. This is the function activation record of choose. Okay. So this is this guy's activation record. Okay. So here is Z, F1, and F2. Z, F1, and F2. Z is -3. F1 points to the squaring function. You can see here F1 is the x times x function, and F2 points to the cubing function, and you can see F2 points to y times y times y. So here's see, this picture here is exact. Now notice that this guy here is missing from over here. That's because this activation record's not in the chain. Right now, this guy is chained to the global frame. He's not showing you the chains on the right. This guy is chained to that guy. So if you don't find something in the global environment, you look in the, I'm sorry, if you don't find something in the local frame, you go to the global frame. Just like here. So if you don't find something in the local activation record, if you don't find something in the local environment, you look in the global environment. So this shows you how they're chained. This guy's chained to that guy. This guy is chained to that guy there. The F is really not playing any role at this point. Right now, the F is sitting there because we called choose from within F, but the choose environment is tied to the global environment, not to the F environment. This is a little bit misleading. This is not a stack. You don't go from here to here to here. If you're looking for something, you don't look in here, then look in here, and then look in here. If you're looking for something, you look in here, and if it's not in here, you go over to here. That's the chain. That's how JavaScript would do it. So there again, their picture here their picture can mess you up if you don't really understand what's going on. This looks like maybe it's a chain where you go a stack where you go from here to here to here. See here over here we say no, this environment is chained to that environment. If you're looking for something you don't find it in here, you find it over here. Okay, right. So okay, so now we're at line 4. We're executing line 4. This is the code that chooses whether to return F1 or return F2. Okay, the F function needs to know whether it's going to call squaring or cubing. So first it calls choose to choose squaring or cubing. So now choose is going to return either F1 or F2. Okay, so now we're returned back to F. Okay, now he doesn't show you the return value, but F now has got its function it could use to call either squaring or cubing. See, now here it calls squaring. See? So F actually called squaring. So the choosing function returned the square function. Okay. So now we're executing the choose is chosen square, and now we're calling square of W. Over here, that's this next thing. Okay. It doesn't really show it here. We're calling the squaring function with the parameter 3. Now here, the problem here is I'm not showing what function is being called here. I've been trying to think of a clever way to demonstrate that. This is a function activation record. It is actually the activation of the squaring function, but I don't show that here because I haven't been able to come up with a clever way to show that. Okay, so it got that value back from the choosing function. So it's calling what it got back from the choosing function. So it's calling the squaring function. I know that, and with parameter -3. So here they show it better. You're calling the squaring function with parameter -3. Here I just say you're calling some function, and I can't think of a clever way to get the name of the function in here because the name doesn't mean anything actually. Unfortunately, the name isn't really meaning. I could possibly just put the source code in. I could put a pointer to the source code, but that would make this thing grow really possibly too big to read. So I just leave it function activation record. You have to trace it yourself to figure out what function is being called. We're calling the function returned by the chooser. Okay. So this is this activation. Okay. Then step through another step here. That's going to return because that's just calling it's calling the squaring function with just the -3, so it's going to return 9. See here it shows you it's going to return 9. Okay, that finished the call to F. See, the choosing function was the return. Yeah, so F returned. It's not F. Actually, that return value. Oh, that's F's return value, not the squaring's return value. Actually, that was F's return. F is just returning what the squaring function returned to it, but that return value is actually F's return value. Okay, so now you're going to log 9. Okay, now you log 9 and you go. That logged 9 in line 8. Now we're in line 9 and we're doing it again. Well, we're going to do the whole thing again with a z of 3 instead of a z of -3. So now we're going to go through all this stuff again, and we're going to go through it 3 times. See, all this stuff is going through the steps we just did 1, 2, 3 times. Up here, it would be, we're going through call F once, call F a second time, call F a third time. So we're just going to, so we get all this output here because we're just going to do it over and over again. Okay. Notice that if you really work at it, you can see a one-to-one mapping between the visualization over here and the visualization over here. They're doing the same thing. And this works because this is a JavaScript program that's a simple program. It's not really using closures. So it essentially is JavaScript as language 7, JavaScript as C. Because remember, this is also the C program. Okay, so this is the part of JavaScript that just mimics C, doesn't use closures, because we're not needing the feature of a closure here. We don't have any functions with these functions don't have, none of these functions are open. Every function is closed. So that function has no non-local references. That function has no non-local references. That function has no non-local references. All 4 of these functions are closed. As expressions, they're closed expressions, no need for closures. If you have closed expressions, you don't need closures. Okay. So when JavaScript, now this debugger was probably written with this case in mind, because if you're teaching JavaScript, mostly you avoid the closures. Unfortunately, when people teach JavaScript, they don't teach the hard parts, the parts that get used in the real world, the hard parts. They tend to emphasize the easy parts. So if you look at JavaScript courses in a lot of introductory JavaScript books, they don't talk about closures. They treat that as an advanced topic that you'll never learn. Okay, but the trouble is closures are really important these days. But the tutor kind of, as we'll see when we get to where you do need closures, the JavaScript tutor doesn't do them very well. It really was designed around the C part of JavaScript, up to but not including the closures. And the C tutor, it's not the visualizer's fault. There's just no clear way of how to visualize these function pointers. What are you going to do? Point at binary code? There just is no good idea. Nobody's got a really good idea of what should happen here. If you ran this C program in a real C debugger, if you wanted to follow that function pointer, I don't have one. I haven't used the C debugger in a while, but when you, like in Visual Studio, if you do this, if you do it in Visual Studio, if you follow that pointer, it'll literally point you to the binary code. That's exactly what and then, I used to do this in the architecture class. When I taught architecture, I would do this kind of stuff. If you followed one of these function pointers, it would take you to the binary code in memory of the function, the compiled function. And then it could disassemble it to assembly language. Okay, so depending on the level of the debugger, it would either point you at machine code or point you at disassembled assembly code. Some of the debuggers would point you at assembly code, and some of them would literally point you at machine code. But if you followed the function pointer, it would just point at the location in memory where the code is, and it would either show you binary, machine code, or like I said, or disassembled assembly code. Okay, and I think Visual Studio can sometimes decompile that code to C, but then then it gets kind of iffy because the compiled code in memory isn't one-to-one mapped back to the original C, because it's usually optimized. So it actually doesn't map back to the original C code, because the code that's physically in memory has been optimized. So it may no longer look like the original C code. Okay, so the C visualizer is kind of stuck at this point. This is a legitimate C program, but again, nobody teaches this in an introductory C course. People don't use function pointers in introductory C courses. Function pointers are ubiquitous in modern C programming. Real C programmers have to use function pointers all the time. You can't write anything of sophistication in C these days without using function pointers. Okay, so the real use case for C is almost entirely in using function pointers. When you're if you're going to use C to write a compiler or an interpreter or a database system, you're going to need function pointers left and right. But the visualizer is a tool for teaching, and for the most part, function pointers aren't part of the teaching. Okay, okay. Now let's go back to the version that uses closures. Now let's compare theirs to ours, our language 8. Okay, that was this one. Okay, so now what I said was the same thing. They're treating this as if it was language 7. So that function name points to that code. That function name points to that code. That worked for the language 7 versions. It doesn't work here because you're just stuck there going, what's X? That's an open function. It's not closed. It needs a closure. The closure was over here, but that's not the closure either. The closure really is that box with X's 5 in it. See, that's not the closure because what X? That's still, this X is that X, but what value does it have? The value it has is this X. That's the closure. The closure is this guy with that guy together. That's the closure, the two of them together. Okay. When they got to here, add 5 should be pointing at that box that was down here. And then that box pointed at this function. That would, if you want, that would be the closure. Though the way it's usually implemented is this is not the closure. This is the environment. So this guy is half the closure. The closure is the closure is just that. The closure is not this return value. The closure is just that. So this arrow is kind of misleading. This arrow is what the function's returning. The closure is that X is 5. Well, in a way, this is the closure. It's this guy combined with that arrow, but it's usually thought of as two things, not one thing. Okay, so that's how we have it over here. The closure is IPEP, instruction pointer, environment pointer. Instruction pointer is that arrow, environment pointers to that box that disappeared with X equal 5 in it. I don't have a good way of visualizing that over here. I just call it an IPEP pair. Over here, if you want to know what that is, you open IPEP in the source code. And you see it's 2 pointers. A tree pointer, which is the code pointer, and an environment pointer, one of those boxes that holds a value. Okay, so the IPEP is 2 pointers. That's one of them. And the other one's missing from this picture. They should have I wish they'd come up with a way of making that box not disappear and then actually showing you either 2 arrows coming out of here or an arrow going to an intermediate box, which is the IPEP object, and then that IPEP object holding 2 more arrows. See, the IPEP object holds 2 more arrows. See, so you point at this object and it points at 2 other objects. That's the way it should be. You point, which is what this says. You point at the IPEP object, and then the IPEP object points at 2 more objects for you. Okay, that's the way it should be. But I don't have a way of pointing at all these objects over here. So I just say value L points to the IPEP. Add 5 should have pointed to a box with 2 arrows coming out of it, 1 arrow to the code and 1 arrow to the X equals 5. All right. Way it is right now, you don't have a clue what X is. Okay. Now, but watch what happens as I step through this code. Okay. Okay. Now I'm going to call make adder again and build the add 10 object. Same problem. This is the closure that's going to close off the add 10. This is the closure for that guy. Notice that this guy and this guy look a lot alike. They're the exact same thing. They're just copies of this. Now what's going to happen here is, now watch this, how bad this is. Add 5 is this. Add 10 is this. They look alike. So why aren't they the same thing? Because Each one has a hidden piece that's missing in the picture, the closure. This one's closed by x equals 5. This one's closed by x equals 10. Each one of these has a different closure. This one is supposed to be pointing back at this box here. And this one's supposed to be pointing back at that box there. But those boxes disappeared on us in this visualization. So you're left with this flaky visualization, which could actually do more. If you're trying to teach, this could do more harm than good, because there's clearly something missing here. And if you read enough Stack Overflow things about closures, you'll realize that people don't understand what's going on here. Visualizations like this screw people up. They start writing very strange things in Stack Overflow answers about what closures are, because things like this don't help. There's so many misrepresentations of closures out there that just end up doing more harm than good. There's a big hole in this visualization. Okay, so add 5 is really pointing at two things. X equals 5 is over here. Add 10 is really pointing at two things. X equals 10 is really over here. In our case, it's a little bit better. Here is this picture here. Add 5, but see here, add 5 is two things, IPEP, and add 10 is two things, IPEP. Unfortunately, I can't visualize what the IP and the EP are, but at least I'm warning you that add 5 is two things. It's an IP and an EP. And you know what those IPEPs are two things, because you go look in here and say, oh, an IPEP points to two things, code, environment. Okay, right? But this block here is this stage of the code. Okay, now you call add 5. Now at this place, now watch what happens when we call add 5 in the visualizer. Here's the closure reappears in a weird thing. Parent, x equals 5. Where did they get the word parent? I have no idea. It should have said closure, x equals 5. Why they called it parent, I haven't a clue. Now it's still misleading, but and again, they're not showing you that they're executing. So right now, see, we're doing add 5. We're calling that function with that closure.
Well, Professor?
Yeah,
Could they possibly be calling it parent because that's the environment that it came from?
Yeah, I think
where it closes it?
Yeah, I think that's what they're thinking of. Yeah, you're right. That's what they thought it is. See, that's this thing here. That's the parent environment that's wrapped around here. So yeah, they're using the word parent because it's nested. So this guy was pulled out of this guy, which is the parent. But the trouble is, both these have the same parent. What do I mean by that? Him and him have the same parent.
Right.
It's this guy. It's not the parent that's important. What is important?
The closure?
Which is?
The 5.
The what? The 5, yes. The 5, not the, yeah, it's the 5. It's the X tied to 5 that's important, not that it came from up here. So yeah, it is, yeah, you're right. It's clear where they got the word parent from, because it's the outer environment, it's the outer lexical scope. Okay, it's the outer scope. They could have called this outer, they could have called it parent scope. It's the outer scope. But both of these have the same outer scope. So that still doesn't help you. What's the key is the X. That part they got right. It should have said closure with X equals 5. You're closing this guy with X being 5. Now, they've lost the pointer to this word. Now, we have to know here that we're in call add 5. So we're in this function with this closure. Now, if this guy had pointed to his closure, then it'd be clear that we'd be executing this guy with his closure. See, they should have been bundled together. Okay, so where he should have used the word closure, he uses the word parent. Yeah, it's obvious where he's getting the word parent from, but I still think it's a bad choice of words. Okay, it's because parent implies this outer scope, and over here, that's the outer scope that this guy is nested in. But the closure isn't that outer scope. The closure is that outer scope holding X is 5. That's the key. It's really that environment. It really is that box there. That box is the closure, and it's not the parent. See, it's that box. Okay, it's that box. It's the that box with that code is the closure. That box with that code is the closure. Okay. 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 So now, with a little bit of effort, you can make sense of what he's doing here. So he's calling this function with the X closed with 5. Okay. So he's going to end up returning 7. 5 plus 2 is 7. Okay. So we're returning X plus Y. Y is that local variable. X comes from this, what he thinks of as the parent scope, but it's not coming from the parent scope, it's coming from the closure. Okay. Then you call the other. Now notice it just says parent X10. So, but now you're calling this closure. See, you're calling this closure, not that closure. You're calling this one now. And it's this one with a different, with a different closure. This is, you have to really know what you're doing to make sense of what this visualizer is telling you. The visualizer is leaving a lot unsaid. So, I think to really, if a student comes in and starts watching this code, I think they're going to be totally flustered, because I don't think the visualizer is helping them much here, because it's not showing the closures in any way well. Now, over here, I think I do a little bit better, not a whole lot better, because I don't have a GUI to work with. But over here, let's see. We said this one here was, let me see if I can find it now. That was this one. Okay. You've got make adder, add 5, add 10, all set up. Okay. That's here. So that's at the line of code. That's after executing these 2 lines. And that's when you're about to execute this one. Okay. Now, we're about to execute add 5. We're about to execute that guy. That's here. That one is this. Okay. Now, this little muddled mess here, at least over here, is a little bit clearer. Y is one environment. X is a different environment. X came from the closure. Y comes from the function call. They are different pieces of the puzzle. Here, it's just one box with Y is 2 and this parent notation saying that X is 5. This is more accurate over here. You called function add 5 with parameter Y equals 2. So that's an activation record. That's this activation record. That activation record was calling a closure. The closure holds another activation record. There's the missing box that this guy's not showing, that he kind of puts in. He makes it look like it's part of this box. But this box up here was supposed to be over here out on the side. Remember, it was tied to this guy. He was paired with that guy, the closure. So that X equal 5 really was from over here. And here I showed it as a separate environment. See, that environment was what the closure pointed at. Then the closure was chained to the global environment. Okay. Now, I'm not going to really be using it in this case, because I don't have, if one of these variables was a global variable, then this function here would have a local variable, a closure variable, and a global variable in it. And we could have done that example. I could have created a global variable and had this thing return X plus Y plus Z, and Z be the global variable. y would be the parameter, x would be in the closure, and the third variable could be a global variable. And then that would show up here as local variable, closure variable, global variable. See, there are three places that variables can come from. They could be a parameter to the function, they could be part of the closure, or they could be in the global frame, because there's really three pieces here. He doesn't have three pieces to this. Yeah, this is kind of muddled, I think. Okay, there's really kind of a muddledness to this. Okay, and if I wanted to really demonstrate that muddle, I would put a global variable up here called Bob or whatever, and have this function return x plus y plus Bob. Then this function would be using both a local variable, a closed off variable, and a global variable. I don't know how he would visualize that over here, but probably not. I probably wouldn't change the visualization at all, but it would be a little bit weird. You wouldn't realize that at this point he's getting variables from three different places. The Bob would show up in the global frame, and you'd be getting y from one frame, x from another frame, and Bob from a third frame. But that's clear here. There's the frame that's the activation of add 5. See, we're calling add 5. There's the frame that's the activation of add 5. There's the frame that was the closure from calling make adder, and there's the global frame. Okay, so this box here is this picture here. Okay, and you can see y is 2, x is 5. Y is 2, x is 5. Okay, now the next thing here is, well, he returns 7. Okay, now he's ready to call add 10. Okay, over here, oh, see, now here was the return value, return 7. So if I step back one more, my return 7, whoops, where did I lost? My return 7 is here. The return value is 7. Okay. So after that, I'm ready to call add 10. So here's calling add 10. That's this box. I'm calling add 10, which is using the 10 closure with parameter 2. Okay, so this is this picture. Okay, and it's going to return 12. Returning 12 is, well, this 12 down here. See, then we're done. That's pretty, we finished. See, so each step here had an exact step over here. This is the final, this is the final frame. This one here, okay? Where where's the outputs? Where did the output go up? Now I've lost. Where did this thing print? Oh, I didn't print anything. No, I never did. Yeah, I didn't. Yeah, I didn't. I forgot to. I didn't console log these guys, so they didn't get. They returned and then they were disappeared. See, I didn't console log them. If I actually, I've got one little goof up here. Let me just show you real quick. See how I'm saving the return values and variables? I should have made this var r1 equal and var r2 equal. That would make them more. Yeah. Here I saved the return values. Here I should have saved the return values. See, there's R1 and R2. Now that is here. See, there's R1 and R2. See, now this environment is exactly that one at the end. That's the end environment. Okay. I'll update. I have to remember to update that thing. Because I made a little change in one of them and forgot to make the change in the other one. Okay. So JavaScript and language 8 are the same. The hard part is trying to visualize and think about this stuff. The hard part is trying to understand how the language works. This visualizer shows you one way. Now we run out of time. The next thing to show you was that we'll do this on next week. It's because I think it's well worth it, because JavaScript's the language you guys can probably end up making money on. If you want to make money these days, go learn JavaScript. That's the language that people are using to build the internet. Okay, so learning how this is working in JavaScript and then using this as a model for the JavaScript is real well. If you can switch to the JavaScript console, you can take this example. Just see, I take this example and I copy it, hit F12, open the JavaScript console, and punch that code into here. See, I've now defined make adder. It's a function. See, make adder is a function. See, and then I could call make adder. Now run out of time, but I can do this I can do this over here. Okay, add 5 is a closure, but it doesn't show me that. If I want to see add 5 is a closure, I type log. No. It's this console.dir. I have no idea why you call it dir. There's the closure. There it is. It's kind of messy, but there's add 5. There's the closure finally. There's the EP. Okay. There. See, there is the closure. Finally, it shows you that that this add 5 is closed over by, see, it's closed over from make adder. Make adder was the source of the closure, and the closure is x equals 5. Okay, so the closure came from there, and that's its value. So we'll quit there. But the JavaScript the JavaScript debugger, the real Google written JavaScript debugger, which is hard to use, it actually shows you the closure. Again, they don't have a great way to show it either. Over here we show it one way. Here they show it. Notice it's buried deep inside of all these little triangles, and you have to use this special function to see it. If you just ask it what add 5 is, it shows you it shows you like the Java visualizer did, just the code. It doesn't show you the closure. By default, it wants to show you just the code, not the closure. You have to work harder to get it to show you the closure. The Java visualizer doesn't seem to have any way to show you the closure that I can find. The debugger will show you the closure if you ask hard enough. It initially just wants to show you the IP, the instruction pointer, and it doesn't want to show you the EP. To see the EP, you got to go dig deep for it. See, under scopes, there's the closure. See, 3 levels down. Okay, so we'll quit there. It's interesting. I mean, this debugger is where people do all their work these days. If you're writing heavy-duty JavaScript code, you're doing it in this debugger. This is the debugger that's built into Chrome. This is called DevTools. This is called the Chrome DevTools. Okay, and I'm not sure how many of you have worked with this, but it's called Chrome DevTools. Okay. Oh, Chrome DevTools does not display closure. That's actually not true. It does show the closure if you dig deep. And the answer to this Stack Overflow question is you got to dig deep enough to find the closure in the DevTools. Okay. So this is kind of interesting. What we're doing over here really is part of modern programming. I mean, that's probably why I'm beating this to death. I want you to see that what we're doing over here is a simplified model of something that's very complex that is part of real programming. It's part of Chrome. It's part of JavaScript. They've got their way to try to visualize it. Over here, we have a way to try to visualize it, because visualizing it is how you understand it. Okay, we've gone over, we'll quit there. And on next week, we'll keep playing with this. I think, because I think comparing language 8 to JavaScript is pretty good for you, because you can see how language 8 is a model of something that's out there in the real world that's important. Okay, anybody, any last question? Any question? Play with this stuff. Try to, try to match this to this like we did here. It's tricky. It takes real effort. It takes concentration. I can do it because I've been concentrating on it a lot lately. It takes effort to match these things up. But if you're actually writing real code in a real job and there's a bug, this is what you're going to do. You're going to be sitting there staring at this stuff, trying to figure out what it's doing. And and if you've done it here, it'll help you when you need to do it in a real environment. If you've sorted through these baby examples, it'll help you in the future if you have to deal with much harder pieces of code. Okay, so we'll quit there. So have a nice weekend. See you on Monday. Bye-bye.